Welcome to this explainer. Let's get right into it. Whenever we look at those massive steel titans towering over industrial plants, pressure vessels, right? It's easy to just see a giant metal tank, but there is a completely invisible, incredibly powerful battle of physics playing out right inside that metal. Today, we're going to uncover the unseen internal forces that completely dictate the design of a pressure vessel's most critical component. By the end of this, I promise you, you'll look at these massive structures in a completely new way. So let me ask you something. Have you ever wondered what actually dictates the cost, the insane weight, and, most importantly, the safety of a pressure vessel? If you're relatively new to plant mechanical engineering, it might seem like you just pick a really thick piece of metal and kind of hope for the best. But there's a delicate, high-stakes balancing act happening behind the scenes. Our goal as engineers is to save money and reduce heavy material weight without compromising a single ounce of safety. And the key to that whole balance, it lies in one specific part of the vessel. Okay, let's dive into the core of the whole thing. That massive, cylindrical section right in the middle, sitting between those two curved ends, that's called the shell. It's literally the heart of the pressure vessel. Because of its sheer size and volume, the shell makes up the vast majority of the vessel's total weight, which means it eats up the biggest chunk of the manufacturing budget. So the mechanical engineer's ultimate challenge is figuring out how to calculate the design so that this massive steel plate is as thin as mathematically possible while still guaranteeing absolute safety. Now, to nail down that perfect, safe, optimal thickness, we've got to understand what this metal is actually fighting against. There are two competing, completely invisible forces, internal stresses, that are constantly trying to tear this steel cylinder apart from the inside out whenever it's pressurized. We call these circumferential stress and longitudinal stress. To design a safe shell, we have to account for both of them. First up, let's look at circumferential stress, or as you'll hear it called on site all the time, hoop stress. Imagine the liquid or gas inside the vessel expanding as it heats up. Circumferential stress is simply that outward pressure, pushing directly against the cylinder walls. It's a force acting perpendicular to the axis of the vessel, and it is literally trying to burst the shell sideways. So, how do we actually engineer against this? With a surprisingly elegant formula. To find the required thickness of the steel plate, which we'll call T, we multiply the internal design pressure, P, by the inner radius of the shell, R. We then divide that outward force by the allowable stress, S, of the specific steel we're using. Allowable stress is basically how much tension the metal can safely handle before it fails. So, thickness equals pressure times radius divided by allowable stress. Keep an eye on that S on the bottom. It's going to be important in a second. All right, let's pivot to the second force, longitudinal stress. While hoop stress pushes outward on the sides, longitudinal stress is the internal force pushing against the vessel's closed ends. It pushes straight along the central axis of the cylinder. Think of it as a force trying to stretch the entire steel plate lengthwise, pulling it apart from end to end, almost like a giant metal rubber band. And here is the math for surviving that lengthwise stretch. Look really closely at the denominator here. The variables on top are exactly the same, pressure times radius. But to find the required thickness against longitudinal stress, we divide by 2 times the allowable stress, or 2s. Now, what's really fascinating when you compare these two formulas directly is what that little 2 actually means. See that 2 hiding in the bottom of the longitudinal formula? In the world of fractions, dividing by 2s means the resulting thickness requirement is literally cut in half. Mathematically, this proves something incredible. The force trying to burst the vessel sideways, the circumferential stress, is exactly twice as strong as the force trying to stretch it lengthwise. Because of that, circumferential stress requires exactly twice the thickness of steel to stay safe. So, what does this all mean in the real world? It means these two stresses are not equal. One is completely dominating the other. Let's do a quick thought experiment. Imagine an overpressurized vessel. If the pressure inside goes completely off the charts beyond all safety margins, how does the shell actually fail? Does it pop its ends off, or does it rip down the middle? Well, think about a cheap plastic water bottle. If you put your mouth over it and blow forcefully into it until it pops, no way does the top blow off, right? The side bursts every single time. Why? Because the sideways stress, the circumferential stress, is mathematically twice as strong. It's a perfect everyday analogy that proves this complex engineering math holds beautifully true in real life. Okay, theory and math are great, but how do we actually build this thing?
Transitioning from equations on a computer screen to actual physical fabrication is a whole different ballgame. How do we take massive amounts of steel and forge a component that can survive those competing forces?
You can't exactly just pour a giant steel tube. The physical steps are straightforward, but they require immense mechanical power. First, we take a massive, flat steel plate, cut perfectly to our calculated dimensions. Then, we literally force that incredibly thick plate through heavy-duty mechanical rollers to bend it into a perfect circle. Finally, we apply intense, specialized welding to close the gap where the two edges meet, creating a single, solid, cylindrical tier. When you look at how it comes together on the shop floor, it all starts to make sense. That long, straight weld running along the length of the cylinder, that's the joint from our rolled plate, known as the longitudinal seam, or long seam. But one rolled plate is never long enough for a whole vessel, so we have to stack multiple cylinders end to end. The circular welds connecting those stacked cylinders together, those are your circumferential seams, or circum seams. And here's where it gets beautifully ironic. Think about the direction of those welds versus the forces we just talked about. The vertical weld, running lengthwise, the long seam, is actually the one fighting the outward, horizontal circumferential stress. Meanwhile, the horizontal, circular weld, the circumseam, is the one fighting the vertical, stretching longitudinal stress. The vertical weld fights the horizontal stress, and the horizontal weld fights the vertical stress. It is a perfectly interlocked defense system. But honestly, realizing all of this just leaves us with a profound appreciation for these massive industrial titans. If a single weld has to hold back forces that can pop steel like a thin plastic bottle, you kind of have to step back and just appreciate the responsibility of the engineering here. The next time you walk past one of these towering vessels, you'll know exactly what invisible battle is playing out right beneath the surface. Thanks for hanging out for this explainer. Keep questioning how the world around you is built.